Hi everyone, my name is Fan Zhang and I'm currently a Chinese undergraduate student from Southwest University. In this video, I'm going to go through something about our paper, Multi-Objective Discrete Moth-Flame Optimization for Complex Network Clustering. I will give the introduction from the following 5 parts. That is our research background, the related work, the proposed method, experiments, and the conclusion. In the real world, many complex systems can be abstracted as a complex network. The social network, protein interaction network, transportation network, and World Wide Web are all quintessential examples. In these complex networks, nodes denote individuals, and edges between nodes represent the individual connection. Numerous researches indicate that community structures exist in most of the complex networks. That is, the connection between nodes in the same community are tight, but that between different communities are relatively sparse. Community structure rarely represents the set of nodes with the same attributes or similar roles. Community detection, namely the network clustering, can explore the internal structure and functions of the networks. In addition, it can also detect the hidden rules and predict its action. It is essential and critical to network analysis, and it enjoys significant theoretical meaning and wide application prospects. Network clustering can be formulated as a multi-objective optimization problem. The multi-objective optimization problem is to optimize several contradictory problems simultaneously. Specifically, the KKM function aims to maximize the internal links, while RC minimizes the external links. In the past decade, numerous multi-objective optimization algorithms have been proposed for solving network clustering problems. The multi-objective optimization functions can be roughly divided into 3 categories. The first category selects the community score and community fitness as the objective function. The most representative one should be the MOGA-net algorithm proposed by Pisser. In the second category, KKM and RC are selected as the objective functions, like the MODPSO and QDMPSO algorithms proposed by Gong. The third category chooses the NRA and RC as objective functions, such as the MOEA-DNet algorithm proposed by Gong. However, a problem stands out in these algorithms. These algorithms cannot achieve a good balance between exploration and exploitation. Unfortunately, the balance of exploration and exploitation directly affects the network clustering effects. In view of this, our multi-objective discrete Moth-Flame optimization method has been proposed to solve this problem. Now, I will explain our DMFO core idea to all of you guys. Since network clustering is a discrete optimization problem, we can firstly discretize the initial MFO algorithm for the representation of the networks. After that, by redefining the SFS strategies and SFG strategies from the original MFO so that KKM and RC objective functions can be optimized, and then iteratively optimize such functions, the final network clustering division can be acquired. The representation problem of discrete positions is essential for MFO-based optimization, which is a key step for an algorithm to encode the scheme of a solution. Currently, there exist 2 mechanisms for representing discrete individuals: the locus-based representation mechanism and the label-based representation mechanism. The label-based representation method is more intuitive and easier to decode. which has lower computational complexity than that of the local space representation mechanism. Thus, our DMFO chooses the label-based representation mechanism to represent discrete individuals. The node labels of discrete individuals are the cluster the node belongs to. For instance, the graph will at first be encoded based on the label mechanism. Following that, the final solution can be obtained. Finally, we decode the network clustering division. Here, the nodes 1, 2, 5, 6, 7 encoded as 1 belong to one cluster, and the node 3, 4, and 8, which are encoded as 2, reside in another cluster. When designing SFG strategies to avoid the solution falling into the local optimization, we mainly take two strategies. The first one is the neighborhood-based two-way crossover, and the second one should be the neighbor-based mutation means. The neighborhood-based two-way crossover is as shown in the sample graph. For each population individual, we choose another individual in the same population to commit two-way crossover. In this way, two individuals generate, and the better one can be retained. The SFS strategies designed in our method aims to commit efficient search in the solution space. Specifically, we enable the MERS to search in the solution space by redefining the way the moth flies around the flame. Here are some concrete examples. By representing the moths and flames as discrete individuals, the moth can explore the solution space by flame, and the final network clustering can be acquired. In our DMFO method, an improved Chebyshev decomposition method with 12 norm constraint on direction vectors is used to decompose the multi-objective optimization problem into a set of scalar optimization superproblems. This improved method has proved its ability to obtain better Pareto solution and make the final network clustering division more superior. For the real-world networks in real known community, we simultaneously take the majority Q and the normalized mutual information NMI as an evaluation matrix. When it comes to the synthetic datasets, only Q is used for evaluation. For Q and NMI, the closer they are to 1, the better the clustering effects are. To effectively verify the performance of our method, we take the synthetic data sets, that is, the extended Gervin-Newman benchmark, and for real-world networks as our testing data sets. The clustering effects in both synthetic networks and real-world networks are as shown in the figure. It's not difficult to see that both synthetic networks and real-world networks our method can achieve more outstanding clustering effects than all other 7 comparison algorithms. This illustrates that the method we proposed is effective and surpasses all other comparison algorithms. To sum up, we mainly propose the dynamic Moth-Flame optimization for solving network clustering problems. The proposed DMFO can achieve a good balance between exploration and exploitation when redesigning the SFS and SFG strategies in the original MFO. Meanwhile, we utilize an improved Chebyshev method to decompose the multi-objective optimization problems. In this way, a better Pareto solution can be acquired, which can better our clustering effects. Finally, the experiments on the synthetic and real-world datasets can also verify the effectiveness and outstanding performance of our DMFO method. Thanks for your listening. If you have any questions, welcome to contact us, and it's our pleasure to give you some more detailed descriptions. Thank you.